Okay, so we are talking about categorical predictors. How can we incorporate them? Your qualitative variables or categorical predictors can have multiple categories. They may have three levels. Three levels means there are three groups. Let's say a small, medium, large. They may have more than three groups. But when you have to incorporate them in the regression model, then you need to convert them into dummies. Means either you convert them into dummy variable in Excel only, or if you are doing analysis in R, then there is no need to do this. R will do the trick. It will automatically convert your qualitative variable into dummy variables. Now, what are dummy variables? Simply, they are indicator variables. If something is present, then they take on the value 1. And if the attribute is missing, they take on a value 0. For example, let's take gender. So, yes, we need to remember that your dummy variable can take only two values, 0 or 1. Okay, so let's say there is a variable gender, and let's say it has only two categories, male and female. Now, how can it be incorporated in our regression model? Then you need to represent this gender variable in the form of 0 and 1. And you can classify anyone as 0. Either male can be denoted by 0 or female can be denoted by 0. Of course, the other category will be denoted by 1. Let's say there is another variable. Let's say location. And there are, let's say, three locations, A, B, and C. Now, how can we incorporate this? First of all, because this is a qualitative variable, A, B, and C, we cannot enter it directly. So we need to convert it into dummy variable. But there are three categories. It means we can have at most three dummy variables. We can have three dummy variables. One, when A is present, B and C are absent. Then second, when B is present, A and C are missing. And then when C is there and A and B are not there. Okay, so we can have three dummy variables. We can call them like a D1, D2, and D3. We can call them D1, D2, and D3. So D1 can be a dummy variable which takes one for A, 0 otherwise. Okay. And D2, 1 for B and 0. Okay, and then D3, 1 for C. Okay, so we can represent these three categories using three dummy variables. But yeah, one thing we need to keep in mind, when you incorporate these three dummies to represent three levels of one variable, then it will lead to something called perfect multicollinearity, and we call it dummy variable trap. Why? I'm not going into the mathematical details, but if you add these three variables like D1 plus D2 plus D3, then what you will get a series of ones, because this variable is either in A or in B or in C. So D1 plus D2 plus D3 will always take value equal to 1. And if you remember, I told you that our intercept or constant has a hidden variable attached to it, and that variable always take value of 1. So the variable that is there in intercept and this D1 plus D2 plus D3, they all become parallel. They all become the same. So what's the way out? You have got two way out. Either exclude the intercept, drop the intercept, and include as many dummies as are the categories. And second one, which is better, let intercept be there and use one less dummy. Suppose we have two categories, gender, male and female. Two categories, it means only one dummy variable is needed. Next, in this example, location, we have these three dummies. We have three levels, then only two dummies are needed. You can use either D1 or D2 or D2 or D3 or any combination of them, but only two will be needed. And the dummy that we are not including, dummy that we are not including or the category that we are not representing is captured in the intercept. Right. Now, what kind of model can we have using dummy variables? There are two popular kind of models. One we call as the parallel slopes model. As the name suggests, what this model suggests, it says that when we are estimating regression model for different categories, then we are allowing that the intercept is different for different categories, but slope for them is same. Look at this example. Just take at the last example that we did with score 2. So let's say our model is like this, y equals constant plus, let's say, b1 star b2 star x2 plus, let's say we have this b3 star d1 plus error, or I can call it b1. Look at this model. It simply says that y depends on intercept, then x, and then a dummy variable. Now this dummy variable will always take value 0 and 1, right? If the condition is absent, it takes the value 0. Let's say d equals 1 for and 0 for male. Okay. Now, how can we interpret this model? The interpretation of B2 is straightforward. When X increases by 1 unit, then Y will change by B2 units. Y will change by B2 units. Now look at this D. D has coefficient B3, and D can take only one of two values, either 0 or 1. When D is 0, if D is 0, then B3 into D will be eliminated. And what we have, the model reduces to simply y equals b1 plus b2 into x2 plus u. When d1 is 0, okay, when d is 0, then model is simply this, okay. And when d takes on value 1, then model is if d is 1, then y equals b1 plus b2 into x b3 plus u. Why b3? Because b3 into 1, d is 1. Now you can easily see that this b3 is a constant and this b1 is also a constant. So they both will add up. Okay, so they both will add up, and we can say that because 0, in our case, 0 was denoting male and 1 was denoting female. So this model, this one, if d equals 1, it means we're talking about women. So for women, the intercept becomes b1 plus b3. We can write this model as, one second, we can write this as y equals b3 plus b2 star x2 u. This is the equation for women, and for men it is usual. It is y equals to b1 plus b2 x plus u. Notice that in both the cases, the coefficient of x is b2. It means that what we are proposing that for both men and women, the impact of x2 is same, right? When impact is same, it means mathematically we are saying that the slopes are same. When slopes are same, therefore the name the parallel slopes model. Okay, but there is no need. You can just test this assumption as well, whether you need a parallel slopes model or you need an interaction model. So let me estimate this model. In case if you tried a model 2 or model 3, how does it look like? Look at this. Yes, please look at this. Okay, so what the model is, so in this model we have intercept, we have beauty, then is gender male, then age, then beauty colon gender male, then age colon gender male. Okay, so how can we denote this model in terms of equations? So look at this model. Okay, look at this model. I think I did not describe what the data set is code to represent it. Basically, this is real data. The data belongs to University of Texas at Austin. And I think about 92 professors were rated by the students. So the score here represent the evaluation by the students of 91 or 92 professors. They taught several courses. So professors are rated multiple times. Different courses rated professors differently. Okay, and several other variables were measured, like the age of the professor, then gender, then whether the professor belongs to the minority group. Then one team of students was formed. They rated the professors on the basis of their appearance, right? So all these variables were collected, and we tried to find out that what determines the evaluation of a professor by the students. So let's take a very simple model that the evaluation depends on two things, that how good looking the professor is, and second, what is the age of the professor. In this case, what the model will be, a score is equals to beta 1 plus beta 2 age plus beta 3 beauty plus error. Okay, so this model simply says that evaluation depends on two things. Just for example, of course, there are many more determinants and we should consider them all. But for the sake of illustration, to illustrate the use of dummy variable, I'm just considering two variables. Okay, so beauty and age, let's say these are the two determinants. But one can argue that the evaluation of male and female faculties are different. Maybe students view male and female differently. So possible that male professor, when they grow older, maybe they are rated less or vice versa. And similarly for beauty, maybe students rate female professors more on the basis of their beauty. So please don't think I'm stereotyping, just making a case, right? Just for an example. And let's see what the results turn out to be. In this case, they are quite different. So should I do this on R, or I have just run the model and just present the results here? So what do you want me? Should I show this on R? Or this is the same model that I asked you to do at your home? Did you try model 2 or model 3?
Sir, sir, I couldn't try actually. So it's better if you could show it in R.
Okay, I should show this in R. Let's open R Studio then. I think someone is doing some annotations. So please do not try the annotation. It will draw lines here. Okay, let's open R Studio. Okay, so you see, today when I opened the R Studio, it did not open the place where I left it. Maybe by chance, accidentally, I have deleted that file or I have just closed that file. So I opened the R Studio, it says untitled. Now, what can I do? I can locate my R script file and open R Studio from there. Or look at this, I can directly open from here, Control O for open, or go to file, then open file. And then it was in the documents folder. I'm going to the documents. R codes day one, yes. This was the file. And yes, we have loaded it. Okay, second data set. So before it, I need to load the relevant libraries. So let's load the packages. Okay, So let's read the data file. And now we need to read this data file score2. Okay, and look at this command. It says that data2 equals to read.csv, means I want to read this file in data2. Okay, so hit Control Enter. Okay, nothing happens. Let me see on the taskbar. Okay, R session 1, it's here. Okay, we need to browse code2. One second. Yeah, score2.csv. If all goes well, then there must be this variable in the environment data2, because we have loaded this file in data2. Okay. One second. RStudio. One second. Okay. So in case you do not want some of the commands to save for future use, then some ad hoc analysis you can do in console, like I do. Like I want to just see the names of this data file. Of course, you can go to the environment and it is visible from there also. But let's say I want to print the names on this data file. Names data2. Okay. ID, then prof ID, score, age, beauty, gender. There were several other variables, but I intentionally shared just the relevant ones. Okay, so let's make this model. Okay, so look at the basic model. Okay, this basic model, let's run it. And let's look at this. Let's look at this. Let us try to interpret the results. Intercept is 81. Beauty is 1.21. T ratio is 3.55, much larger than 2. And you can see p-value is small, means beauty has a significant positive impact. Means professors who are good looking, they are getting good scores. Then age 0.06, negative value 0.05, 1.15. T value is minus 1.15. It's smaller than 2. And look at the p value 2.5. E minus 1 means you need to shift the decimal place to just 1 point. P value is 0.25, insignificant. So what the model simply says, that beauty is a determinant, important determinant of professor evaluation, but age is not. Okay, but this is not the complete story. Maybe you may believe that beauty and age, they have different impact for men and women. So what we can do means we are saying that the impact of beauty and age is different. So we develop a model like this, where we multiply simply gender with age and beauty. So look at this model. This parallel slopes model first, not the interaction one. First, we are fitting the parallel slopes model. So look at this, simply score tilde beauty age plus gender. Means we are simply saying that age and beauty, they have similar impact for men and women, but the intercept is different. Only the intercept is different. Otherwise, the impact is same. Let's run this model and analyze the results. So look at the result. 1.28. Now you see, once you include male and female, both as different intercepts, then age becomes significant. So the impact of age is minus 0.11 and its p-value is less than 0.05. Now look at gender male. Why it has denoted gender male? Because I included the variable only gender. Why it has coming up with gender male? Basically what R does, it automatically creates dummy variable for us. R has automatically created a dummy variable gender. And in that variable, R has looked for the categories. It found only two categories, male and female. You must be wondering, the data is from University of Texas, Austin, right? Then why there are only two gender categories, right? When they are like raising their voices for different genders, then why they have collected data? The reason is quite simple. This data is like 15 years old in 2007, right? The data belongs to 2007. That's why at that time, only two genders were recognized. Okay, so right now in the recent survey, they have included many more categories. Okay, so look at this. Yeah, so why gender male? Because R has created a dummy variable for us, and alphabetically, it has given 0 to female and 1 to male. Okay, so this gender male is similar to a dummy variable where your dummy variable has taken a value 1. Female is missing, means female is captured in intercept. So what is the intercept for female? This is the intercept for female, 81.13. Slope for both men and women are same. Then 4.02. This is the differential intercept for men. Means the intercept for men is 4 points larger. Significant? Yeah, it is significant. Means the intercept for men and women are different. But maybe one might argue further that even the impact on beauty and age are different for people of different genders. So let's go for the interactive model. Let's go for interaction. Yes,
sir,
please.
Before going to interaction, can you please interpret one more time gender male? How to interpret it?
Yeah, gender male is saying that because we have included in terms of addition. So this is an additive dummy. Additive dummy are interpreted in terms of intercept. So look at the intercept first. 81.13. This intercept belongs to the missing category, that is female. Means what we can do, you can make two different equations, one for male and one for female. If we do this, then the intercept for female would be this 81.13 and intercept for male would be this 81.13 plus 4.02. So intercept plus value of gender male, this is the intercept for men. Okay.
Okay, sir.
Yeah. The second model would be more interesting. Model with interaction.
So in panel data analysis, we also create dummy variable.
Yeah.
So this dummy variable is similar to that, or it is different?
Same. See, why we are including those dummy variables? We include dummy variables to represent two kinds of effects. Either you are talking about time effects or you're talking about entity effects. So for different entities, we want a separate intercept. Similarly, for different time periods, we want a different intercept. Same thing, the same concept, right? Absolutely same. So let's run this model 4. Okay, now look at this. The model, it has been formulated. How easy it is, means we need not create any dummy. Like if you would frame the data in Excel, then you would create separate columns and you would type 0 wherever female occurs and you would type 1 wherever male occurs, right? So that would lead to like a lot of wastage of time. And in case you have several categories, suppose you have 5 categories. For 5 categories, you need at least 4 dummy variables, right? You need 4 dummy variables, exactly 4 dummy variables. So in that case, again, that means you need to insert 4 different columns. But when you're working with R, simply use the variable directly. R will automatically convert it into dummies. So look at this. This model 4. And see, that means it is not necessary if you're running the 4th model, you need to name it mod 4. This name is your choice. Like I can name this model as interactive model. I can call it like I model. let's say I can call it interactive IN underscore MO, right? Interactive model, right? Score tilde. So I have multiplied beauty into age plus and age and gender plus gender separately. Okay. So let's run this. It will create a new model called INMO. Okay. So let's run this. Okay. We do not have anything like mod 4. We have this model INMO. Okay, let's run this. Look at the results. Okay, now you see, we had 3 variables, gender, beauty, and age, but we have like 6 coefficients. Why 6? Let us see. One is your regular intercept. The value is 96. Then beauty, there is 0.02. 0.229. And interestingly, this is insignificant. Okay. Then look at gender male. Gender male is the intercept dummy for male. -22. -22. And this is significant. So look at this. It means if we make separate models for men and women, then the intercept for women is 96, and the intercept for men would be 96 plus -22. So roughly it would be around 73 or 74. 1 second. 1 second. 1 second. Okay. Beauty, then gender male, age. Look at age. 0.34. 0.089, and you see the t-value is large and significant, means age has a negative impact. Age has a negative impact on score, means as professors are growing older, students are rating them less. Then beauty colon gender male. This is the interaction of beauty and gender. You see beauty is appearing twice. One simply beauty, and then this beauty colon gender male. It means it is an interaction of dummy variable when it takes a value of 1. And the value is 2.05, and it is significant. So this gives us a very interesting story against the stereotypical belief that people hold that women are rated for their beauty in academics as well. But here the story is totally opposite. For female, you see, when you have beauty without any dummy attached to it, there is a slope for women, and that is simply 0.02, and it is insignificant. It means that at least the data that we are having, it shows that the score for female professors is not dependent on beauty. On the other hand, for male professors, beauty is a significant variable and coefficient is quite high. You see it's more than 2, right? So for male professors, it is positive and significant. For female, beauty is not significant. Age for women is negative and significant. What about age for men? Yeah, gender male colon age. Gender male colon age. And it says 0.37. And you see 0.112. And this is significant. Very strange results. Look at this. Look at this age and gender male colon age. Age has a negative coefficient of -0.34. It means that as the age of the professor increases by 1 year, a score goes down by around 0.34 points, right? Because it is -0.34. It goes down, but it goes down for women. As women grow older, because of their age, their score goes down by about 0.34 units. And look at for male. For male, what is the impact of age? For men, the impact of age is the coefficient of age plus the coefficient of this gender male colon age. So -0.34 plus 0.37, it takes a positive value, 0.03. So it shows that for men, this age seems to be not important. Or that means there is a huge difference the way students look at old male professors and old female professors, right? It's quite different. Again, we can include several other variables and complete this story, but this is how we can incorporate dummy variables. And like what we mean by interactive dummies, and then only intercept dummies. So slope dummies and intercept dummies. I hope I am clear. Any queries regarding this model?
Sir, could you please explain what is the significance of gender male? You said minus 22.8 is very significant. How is it significant, sir?
1 second. Look at the T ratio. Gender male, 22.8, 6.77. Look at the T ratio. It is 3.36. So larger than 2 means it is significant. Or directly look at the p-value. Do not use rule of thumb. It's better you directly refer to p-values. So 8 point E minus 4, right? So you see the p-value is quite small. It's significant. Is it okay?
Sir, my question is, what does it symbolize? Gender male, what does that symbolize?
Gender male is the dummy variable which takes value 1 for male.
Yeah.
Yeah, it means, let me show you. I have written this model in the form of an equation. Look at this. Look at this equation. So this is the estimated equation. If score equals to this 96 point, this intercept plus the impact of beauty, age, then gender male, and so on. Is it fine? Now look at this. 0.23 beauty. Look at this. Yeah, look at this term. This is the coefficient of gender. So gender can take two values, either male or female. What R has done, R has coded it in alphabetical order. So female gets a 0 and male gets 1. So when we look this model for women, then gender everywhere will become 0. Gender everywhere will become 0, and wherever gender appears, that term will vanish. On the other hand, whenever this model is seen for men, then gender will always take a value of 1. So what will happen? This minus 22 point something into 1. So this will become exactly minus 22. This will become minus 22.75 into 1. So it will become minus 22.775. And this will then merge with the intercept. What is the present intercept? Look at this. 96.20. So the intercept for men will become 96.20 plus minus 22.75. So this way the intercept for men is smaller than the intercept for women. So now what you can do, on the basis of this one equation, you can develop separate equation for men and women like this. Look at this. This is the entire equation for female. For female, just chop away the gender terms. And you see, this is the model for women. Okay, simply wherever gender appears, it takes a value of 0 and it vanishes. And for women, sorry, for male, the equation is like this. So put 1 in place of gender, solve it, and you're gonna get this. The score equals 73.44. This is the intercept for women plus the intercept for gender male, the coefficient for gender male. Then look at this 2.28. This 2.28 is in the original equation, the intercept for beauty plus the intercept for beauty colon gender male. Okay.
Sir, can I ask you one question, sir?
Yes, please.
Like 1 and 2, what could be the result then?
Please once again.
Instead of giving the codes 0 to 1, if we give the coding for male, female 1 and then male 2.
Then interpretation would be difficult, right?
Okay.
Because not difficult, rather it will be wrong. Basically, there is a when we are like making some contrasts, right? That's an entire different topic. when we are comparing means using t-test or some sort of ANOVA, then multiple comparisons, there we have to devise very clever forms of coding so that we can compare. So, but when it comes to like general regression models, it's better you keep it 0 and 1, because this way 0 will become the reference category. 1 and 2 would be difficult to interpret.
Okay.
Will be difficult to interpret, and you cannot just put it directly the way I have done it. Like you see the regression model. Let's go there. Look here, we have simply just multiplied it. If you are giving it 0 and 1, then this multiplication will not work, right? It will give very faulty results.
Sir,
Okay. So now what we can do, like we can just include dummy variables for several things, like for race, for ethnicity, for religion, for region, for user versus non-user, for like anything. And these can be treated as control variables. Okay. And then people who are working in finance, like they can use dummy for day of the week effect, or maybe month effect, or a specific week effect, expiry effect. Dummy variables can be created directly.
sir,
Then I think the other codes are evident. Yeah, please.
if you don't mind, we will spend 1 minute on this, sir. Like in our model, we have a dependent variable as score. Then we have interaction effect of beauty and gender, age and gender, then gender.
Yeah.
So we got the result as beauty is equal to 0.229 as a estimate, and this is not significant.
Yes.
So we can interpret that beauty has no impact on the score. That is clear, sir.
Beauty has no impact on score for women. For women.
Okay, for women. So
because we have interacted it. So when beauty appears with dummy variable, it will be you can say differential impact on male, and when beauty is alone, it is the impact on the reference category. In the present case, our reference category is female. So right now in our model, beauty gives the impact on female. Okay.
So the just variable beauty is talking about the female.
Yeah, reference category. Whatever reference category you want, you can ask R to make male as the reference category. We can do this.
Okay. Then what about this gender male, sir? How to interpret? Like
gender male is simply the change in the intercept. You can see we can have a simple equation. A simple equation like score is equals to beta 1 plus beta 2 beauty plus beta 3 age. Just 3 coefficient. One is intercept, second one is beauty, and third is for age. Right. So we are trying to find out, do these 3 coefficients, do they differ for male and female? So gender male, only gender male is capturing the difference for intercept. Then gender male beauty is capturing the differential differential impact for beauty. And this gender male age is capturing the differential impact of age for men. So wherever gender male you find, this is the differential impact.
Okay, that is for male only.
Yeah.
So beauty gender male is for male. Gender male age is also for
beauty
male.
Gender male is the, you can say, differential impact for male. So the impact for male would be beauty plus gender male colon beauty.
Right. Okay.
Yeah. Age would be age plus gender male colon age.
Okay.
So means if you want to find out the value for male, you need to add 2 values. For reference category, forget the male part, just take up 3 values: intercept, beauty, and age. These 3 values belong to female. Now, what belongs to male? See, when you have gender male, beauty gender male, and age gender male, these are not the values for men. These are the differential values for men. Mind it, differential. Differential intercept and differential slopes. Okay. So look at this, let's say age and gender male. The value is 0.37. So the impact of age on men is 0.37 more than the impact for women.
Okay.
Okay. Look at this simple gender male, that is minus 22.75. So the intercept for men is minus 22.75, different than women. Because this is a negative, so we say the intercept for men is lower than the intercept for women. Am I accessible?
Right, sir. Right, sir.
Okay. Let's move further. Okay, so look at this model. I won't be running it because I have to cover other topics as well. And this belongs to the new data set that is education 2. And see what the model says. What explains the expenditure on education? Expenditure, income, then the number of residents in that particular state, then percentage of young residents living in the metropolitan areas. I did not describe the variables for you. I'll share a file separate. Young residents plus, then region. You see, region is let me show you this data file. If you had inspected this data file, then you will notice, let me show you. Let's read the data file. Just want to show you. Education 2. Okay. And let's look at this file. Look at the first few rows. Head. I've denoted it by educ. Okay. You see, this last variable is a character variable. And one more thing you should do, I just did not tell you this command, but you should use it. You can just, for quick browsing, you can just click on the object in the environment or just type this str within parentheses, type in the name of the object. Okay. And then what does it tell? This is data frame of 50 observations. Then state is 1, 2, 3, 4. Resident is integer. Income is integer. Young residents is integer. Expenditure is integer. Region is CHR. Region is a character variable. Okay. And it takes on values like northeast, then north center, south, and west this way. Okay. So like you may find out, it is possible that states which are in northeast may be spending differently on education than states which are in south or which are in west. So you may hypothesize like what explains the expenditure on education. And then this is another application of a dummy variable. I'm not going into it. So you may try this model yourself because there are a number of other things that you can just do and then cast later on. Yeah, this is the thing that I should talk about. Look at this. Let me make this model. Let us make this model. Okay. So, and look at this. Let's run the Bruce-Pagan test on this model and see what is the result. P-value is small, means your null hypothesis is rejected. Our residuals are heteroscedastic for our education data set. Means there is heteroscedasticity. The assumption of homoscedasticity cannot be maintained. Now, what will you do? So we talked about heteroscedasticity yesterday, that what happens when our residuals are heteroscedastic. Yes, our coefficients are still unbiased. They are still consistent, but they are no longer efficient. Rather, the standard errors are unreliable. When they're unreliable, we cannot conduct any hypothesis test. Now, what is the way out? What will you do? See, first we need to understand what are the causes of heteroscedasticity. What are the causes? Quite possible heteroscedasticity is the result of a missing variable. There is an important determinant which you did not include, and that will be captured in the error term and causing heteroscedasticity. But on several occasions, like whatever theory that you are testing, you have included all the relevant variables and you still find there is heteroscedasticity. Okay, what is the way out? You should do one of the two things, or rather, I would say you should do both the things. You should adjust the standard errors or you should use what we call the robust standard errors, number one. Number two, you should do bootstrapping to generate new set of standard errors and then test the hypothesis again. So let's do it. This was important, that robust estimates. So in Stata, it's quite easy. You run a model and then type robust. In R, it's equally easy. Look at this. Look at this model. How do we make robust estimates? I would suggest you must always do regression twice, one with OLS and second time when you have this, like robust estimates. So we are making model 6. And the function is LM robust. And this function is from the package estimate R. Right? Wonderful package. This has made our life simple. Earlier, this would require at least 2 or 3 steps. Okay. So I have been doing all along. So for this workshop, when I was trying to find out like what could be the easier way of discussing R, then I discovered this package. So syntax is quite simple, LM robust. Then we write the formula, expenditure tilde, then all the variables, and see what we type later on.
Excuse me, sir.
Yes, please.
Sir, in the third data set, resident, the variable resident is represented by figures like 508, 564. So what it actually means, sir?
Basically, this value is, as far as I'm to recall, it was the in that particular state, for every 1,000 persons, how many people are living in metropolitan areas. So in that state, let's say the value is 560. It means 560 out of 1,000 are living in the metropolitan areas. Right? I'll share the variable description. I just forgot to share it. Yeah.
Yes.
That is the like number of people per 1,000 living in the metropolitan areas. Okay.
Okay, sir.
Comma. One second. One second. And the kind of standard error you want. So if you want to replicate the results similar to Stata, you can type SE type equals to quote data. Just enter. Look at this model.
Sir, screen is not visible, sir. Yeah, now we got
Screen
it.
is not visible.
Yes, now we got it.
Okay. Okay, so what you can do, you can compare the results of this LM robust command with the results of that LM. That means compare the results of model 5 and model 6. And you will see the model 6 has retained the same value for the estimates, but standard errors are changed. As a result of this, earlier variables which were significant, some of them may become insignificant or vice versa. Okay, so this is how the heteroscedasticity adjustment has taken place. So robust errors are over. Then bootstrapping is similar to it. I'll just share a simple code. Again, there are several ways of doing bootstrapping. I'll find out some easier way and we'll share the codes with you. Yes, any queries? All the assumptions are over, including what we have covered, testing for the assumptions. Then if assumptions are violated, what to do? It's very simple answer. If assumptions are violated, you should go to the robust errors or go for bootstrapping. And do look for the theory. Is there any important variable that is missing? Okay. Yeah. So any query, or should we proceed to the next topic?
Sir, if any of the assumptions violated, like normality, heteroscedasticity, exogeneity, then we can go for bootstrapping, sir.
Not for exogeneity. For autocorrelation, for heteroscedasticity, for normality, you can go for robust and this, not for exogeneity.
So
exogeneity, we did not discuss. I did not discuss exogeneity yet. I'm going to discuss it now.
Oh. So this robust model would be the refined and final
mostly it was originally proposed for correction of heteroscedasticity.
Okay.
Right.
Okay.
So yeah, there are like several authors have contributed that how can we determine the correct standard errors. So there are several versions. In fact, when you correct for robustness,
Okay.
then there is like one more way. Sometimes what you find that your errors have some pattern. What is the way to detect heteroscedasticity? Two of the tests I have mentioned, BP test and white test.
Right.
These two tests are there. And then you should make a plot of standardized residuals against fitted values. On the x-axis, show the fitted values. On the y-axis, keep either the standardized residuals or studentized residual. They are similar, keep them. And if you find any pattern, likely that heteroscedasticity is there. But one more thing, there is similar concept to heteroscedasticity that we call clustering. Clustering. Think it this way. Suppose you collected data from 100 different schools. You're trying to find out what determines self-esteem of, let's say, teenagers. You collected data from 100 different schools. It's spread across the state. Okay. So I think there is a good reason to believe that students in a particular school, they have something in common, right? The culture, the impact, the discipline of the school may have impact on their lives as well. So it seems as if there are clusters. Let's say from every school, you collected data from 20 students. 20 students from 100 schools. So 20 into 100, your sample size is 2000. Okay. So we can think of there are 100 clusters of 20 each. So there is an option to correct for this clustering impact. So there is no heteroscedasticity, rather there is clustering. In that case, what you do, in that case, the formula is changed a little, right? So we just find out standard errors controlling for clustering. So there is robust option for clusters, and there is a robust option for heteroscedasticity. And there is third one, a robust option to control both heteroscedasticity and autocorrelation. So these three robust options are popular. Okay, should we move to endogeneity?
Yes, sir.
Yeah, perhaps the most important assumption, that is endogeneity. And what it says that your X variable, your regressors, should not be correlated with the error term. Now, how do we know about it? Let's go open a new data file. Okay, let me close this file. Don't save it. One second. Untitled. I've opened a new file. Okay, so we have already loaded the packages, but let's load once again. Tidyverse, library, and this package that we are going to use is estimate R. Okay. So, okay, let's load this data set, and I'm just keeping this data set in X, let's say. Read.csv. Okay. So load this file. One second. Okay, load this file endogeneity 1. Okay. What we have in this, let's look. So structure of X. 1000 observations of 4 variables. We have 1000 rows and 4 observations. Wage, education, ability. Okay, so look at this. You see in several textbooks that you will find that one of this famous example is always there. In fact, many authors have written like papers on it, not just an example. that what is the impact of education on earning? Let's say on wages or earning, right? Means if people, especially in US, you see that education is very costly, especially the college education. So 4-year bachelor's program may cost you in crores. I was looking at University of California. Its BBA program was about 1.5 crores for 4 years. Huge. So many people have attempted to find out that means, is it worth going by paying so much tuition fees? So people have tried to find out, like, what is the relation between number of years of education and wages? Okay. So let's run a model like this. So let's make model 1. So first model, right? I'm calling it M1 simply. Wage, education, and data is X. Okay. And let's look at the summary of M1. Summary or tidy, both will work. Okay, look at the results. This is important. These estimates, the same thing that we print using tidy function. This is another way of printing. Intercept is -59 and education is 13.1, 0.61, 21, highly significant. So this analysis clearly shows that there is a positive impact of education on wages. And how much impact is there? You see, 13.12, 13, right? But there is a problem with this model. The model is that people can argue that education is having an impact on wages. People who are more educated have spent more years in college, university, and schools, so they are earning more, right? But one can argue that there is another variable which is impacting both education and wages. There is something called ability. That ability, or you can say creativity or talent, or maybe some individual specific factors which motivate people to acquire education, and because of their ability, they're able to earn more, not because of the education. This is quite possible. Means third variable, it is impacting both education and wages simultaneously. If this is the case, then it is not possible to find out the impact of education on wages. So how can you say somebody who is earning more is because of the education? It may be because of the inherent talent, that inherent motivation. That inherent motivation may be responsible for increase in wages, not the additional number of years. So this is the case that we say that there is endogeneity. Endogeneity means your independent variable is related with left out variables. For example, there is no real way to capture ability. Can we? It's difficult, though people may come up with tests like IQ can be measured, or some other thing like emotional quotient, or so many things can be measured, and they can be used as proxies, right? But if, let's say, such a variable does not exist, or like this is somewhat fake data, later on I'll give you the exact data that was used by I think Blackburn and Newmark, right? So they have used paper in A-star paper published in 1992. I'll share the paper as well. Then we'll analyze their data set. First, this fake data set, just to understand what endogeneity is, what impact it has. So guys, just imagine, just pretend that somehow you're able to capture ability. Just pretend. In real life, not possible, but to analyze the concept, let's do this. Okay, so make our second model. M2 equals LM wage tilde edu plus ability. Data is X. Then I'm simply tidying it, tidy M2. Okay. One second. Okay. Yes. Okay. Look at this result. What does it show? So how much is the impact of education in this model? It's 7.7. So once we include the relevant variable ability in our model, the impact of education has gone down substantially. Recall, in the previous model, when education was the only explanatory variable, its coefficient was 13 point something, 13. And it is just half in the presence of ability. So what happens when you miss some important variables, and if those variables are correlated with the regressor, this leads to endogeneity. And because of this endogeneity, even your coefficients are biased. You see, that means in a large sample of 1000, the coefficients are biased. They are biased and they are inconsistent as well. Inconsistent means even if your sample size is infinite, the error will not disappear. Okay, so now this is the true impact of education, that is about 7.7. So let's see, in real life, of course, we will not have ability. Then what can we do? What's the way out when we have endogeneity? First of all, let me tell you a very important thing. There is like no true test of endogeneity, right? So we cannot test for exogeneity, whether education is truly exogenous or not. In our model, education was not exogenous. Why? Because education was related to the missing variable ability. Okay. So we pretend that somehow we're able to measure ability, and when we include it, then we see the model is totally different. Okay. Now in real life, you won't be having access to the confounding variable. The confounding variable which is influencing both the regressor as well as the dependent variable. Right. Now what's the way out? The answer lies in the technique of instrumental variables. Instrumental variable, or simply an instrument. So what is an instrumental variable, or what is an instrument? An instrument is a variable which is correlated with the regressor but uncorrelated with the error term. Let me repeat. First of all, what was the problem with our first model? The problem was that education was related to error. Education was related to error. It means that education is endogenous. Okay. What's the way out? Think of a variable which is related to education, which is highly correlated to education, but not correlated with the error term. So this is the real test that people have to come up with instrumental variables. So let me give you a brief history about it. About 150 years back, the technique has emerged from the study of epidemiologists. So what they were doing, someone was trying to find out the impact, whether this cholera is like waterborne or it is due to some other disease, due to some other factors, right? That means, what are the causes of cholera? I think around 1850s or 1840s. I'm not sure. Yeah, around that time. And this example is mentioned in Econometric Analysis, William Green. Excellent book that you can go through, a bit mathematical, but otherwise wonderful book. So you would see that what one author did, he collected data on two variables. Variable one, the quality of water. Water was contaminated versus water was pure. And then they collected data on like who was suffering from cholera and who was not. And they run a regression model and showed that people who are consuming more dirty water, more contaminated water, they are more prone to cholera. But one person challenged this. They said that it is not because of the water alone, saying that this consumption of contaminated water is correlated with poverty. Poverty, people who are poor, they are not able to maintain hygiene. So not only their water is dirty, water is contaminated. In fact, their food and other stuff is also contaminated. Their hygiene habits are also very poor. So maybe not cause of the water, cause of the other factors, other hygiene factors, they are leading to cholera. Possible. And once you explain this, your model is totally wrong. Then the person conducted another study, second person, and he come up with a very interesting instrument. He tried to find out that during those days, London was getting water from two companies. Just two companies were supplying water to the entire London. And it was found that the place where companies were lifting water directly from the river Thames, at one place, the water was contaminated. It was just close to the sewage dump. So that company was supplying some sort of contaminated water to everybody. And that company was supplying water to like just randomly to anyone. So whether the person is rich or poor or middle class, whatever, so everybody was having that contaminated water. And there was second company, its water was pure. And everybody was getting water, including the person who are poor, who are middle class, who are rich. Everybody was like getting water from that. So what the person did, that water, dirty water and clean water, contaminated water and clean water, they are highly correlated with the kind of the company the water is coming from. But the kind of water the person are receiving is not related to this. So they used it as an instrument. They dropped the quality of water as an independent variable. Rather, what they used this as the instrument, the company as the instrument. Similarly, in our case, education is endogenous. So think of a variable which is related to education, but not related to the error. So let's pretend that people whose parents are educated, they are more likely to send their kids for college and university education. So education of father and mother, we have only father education. In next example, we'll consider that case. So let's say you have data on about years of education of your father as well. So we can contend that the education of father is highly correlated with education of a person, but the education of father is not related to the other factors in the error term. So this way, the father of education becomes an instrumental variable for education. Okay. Now the mathematical process is a bit lengthy. Let me just tell you quickly. So what we do, we first do a regression of education on father education, and then we collect the predicted values from there, and those predicted values are used in the original equation. And this technique is called two-stage least squares. Answer is simple. Why two stage? Because in the first stage, you can say you are purifying your endogenous variables. Like education is endogenous, it is contaminated. So we are purifying education in the first stage regression through instrumental variables. Then in the second stage, we are estimating the coefficients. Let's do it. Okay. So of course, that means I can show you both the ways, first stage regression, second stage regression, but that's lengthy. Let's go with the direct results, the instrumental approach to SLS. So to SLS. So let's run a new model, model 3. And the command is instrumental variable robust, IV robust. And what we have, we have wage, then tilde depend on education, and use instrument. What is instrument? Instrument is the father education. Let me see what is the variable of father. Names in X. Addict, ability, FATH, underline EDUC. Okay. Okay, let's run this model. Okay, so let's look at the results of this 2SLS regression. Guys, look at this. Wonderful. Education is now just 7.73. Recall in model 1, what was the value of education? The value of education was 13, right? So using the two-stage least squares, we have removed the impact due to endogeneity, and now this impact is genuine. So this is how we deal with the case of endogeneity. And see, there is no true test for endogeneity. There are a few tests, like Hausman and Wu test is sometimes proposed, but that is only a test, only a weak test. The real thing of endogeneity or exogeneity, it is a logical thing. Means a computer test, a mathematical test cannot tell you. It is the logic, it is the reasoning that will help you decide whether there is endogeneity or not. Okay, now let's take the real data that was used by by Blackman. I think Blackman. Yeah. I'm missing his name. I'll see who were they. 1 second. So let's load the real data. So go to the data once again. So let's read data again. And this time I'm reading this data to, let's say, I'm calling it WW. It's your wish, whatever name you want to give. WW equals to READ read.csv file.choose. Okay. Wage 2. And this example I borrowed from Woolridge, one of the wonderful books, Introductory Econometrics. So let's look at this data. Look at the variables. There are 17 variables. In fact, in the original data set, there are many more variables. I have retained only 17. So wage is there, hours, IQ, addict, expert, tenure, age, married. Okay, so I'll take this opportunity. I think in the last session yesterday, many people asked about control variables. So in the same example, this was investigated by, I think not this one, that would be the next one. This was a model of Newmark and Blackman, I believe, right? So what they did, they used the education of both the parents as the instruments. So how we incorporate this is quite simple. So look at this. Let's make a model. Let's make our IV model. You can give it any name you want. I can call it my model, right? Though it's not a good practice to use such lengthy names, but just to show my model, we are using two-stage regression, two-stage least squares. So L wage tilde, it depends on, let's say, education, and instrument are father education and mother education. Data is WW. One second. Okay. Let's look at this model. Tidy. So 0.10. So this is the impact of education in the two-stage least squares. Okay. So let me take one more data set, and this time we can include control variables as well. Suppose our interest lies only in what is the impact of education, but education may be impacted by so many other variables. Maybe the place where the person is living, whether the person is married or not, or whether the person is black or white. So race of the person, then region, so many factors may be contributing. So let's use third data set. It was used by cards. Again, the data set, that means these all are real data published, and the papers are published in really reputed journals. So third data set. So new data, and let's say this time I'm just calling it simply data. Read.csv. So this card2.csv, and look at the data. Let's see what's there in this data. Thirteen variables. So let me quickly tell you what the variable is. Near C4. So this person card, he proposed that the proximity to college, that means people who are living to colleges and institutes and universities nearby, then they have like lower cost because they don't have to rent another place, they don't have to pay for transportation, and they're more likely to go for a college education. So they would say that instead of father and mother education, we should use the proximity to college as the instrument. Okay. So in their case, they are saying that education is endogenous and the instrument for education is this near C4. That means C4 means the 4-year colleges. There are colleges in US which just offer courses up to 2 years. So near C4. Then EDIC is number of years. Age is the age of the person. Then father's education, mother's education, South, whether the person is living in South, Black, whether the person is Black or not, SMSA, whether the person is living in a metropolitan area. 1 means the person is there in the metropolitan area, 0 means no. Then wage, then experience, then square of experience. Okay, so now what your model says, your model may include many variables like SMSA, that is the region for urban and rural, then Black, then South, then other variables as well. But your main interest lies in the impact of education on wages. Impact of education on wages. Again, education is endogenous because there are other factors which are causing you to acquire education, and the same factors are responsible for your higher wages. Means endogeneity. How to deal with this? Find out an instrument for education. So like some people used the father's education as instrument. Some others used both mother and father education as instrument. This person has used the proximity to college as an instrument. An instrument has to be weird. See, the more weird the instrument is, the better it will be, because then only it will be uncorrelated, right? So you may come up with really interesting ideas that what can be instrument. And there have to be 3 conditions for something to become an instrument. Number 1, instrument must be related with the endogenous variables. And second, that instrument must not be related to the error term, right? And number 3, that instrument must be causing the dependent variable through endogenous variable only. For example, when we were saying the parent's education has impact on someone's intention to acquire education. Okay, means parent education impacts education. And this in turn impacts earning. It should not happen that the education of parents directly influences your earning. If this happens, then your instrument is like not good. And I did not talk about how do we know if the instrument is strong or not. So I'll just explain in this case. Yes, please.
Sir, can you repeat this, instrument?
Instrument should be relevant, right? It should be exclusive and it should be exogenous. Relevant means that instrument must be related to the endogenous variable. For example, we're talking about education. Education is a problematic variable. Problematic means it is endogenous, right? Your right-hand side regressors must be exogenous. If they are not exogenous, they are problematic variables. They are endogenous, right? Their coefficient would be imprecisely measured. They would be biased as well as inconsistent. What's the way out? Think about another variable that we call instrumental variable, such that the instrument variable is related to the education. That is, it should be relevant. Then it should be uncorrelated with the error term, means it should be exogenous. And this instrument should cause the dependent variable through the endogenous variable alone. Means there is no way that the parent's education can influence your earning other than by influencing your education. There is only one path. Parents' education is influencing children education, and children education is leading to higher wages, right? Otherwise, there is no other path. If there is some other path through which the education of parents is impacting your earning, then it is not a good instrument. It will again be suffering from the same problem. That means your instrument would also be endogenous, right? So this is the main thing. How do we find out good instruments? Anyway, let me just quickly explain it.
Sir, one question, sir. Can we equate this instrument variable to mediation effect?
No, not exactly. Mediation is totally different concept. Mediation, you can say that you're trying to find out that this variable is channelizing its impact. For example, let's say you're finding out that that what causes people to leave their jobs, right? For example, in the present case, if we take the example of wages and education, then if you try to find out the impact of, what I must say, you trying to find out the impact of parents' education on wages, let's say. Suppose your original model was impact on wages, impact of parents' education on wages. Then this doesn't happen directly. There is some intervening variable. There is a mediating variable. For example, you can say that, does summer make us drink more water? When temperature is high, then there is a relation between temperature and thirst. Is it so? When temperature is more, we drink more water, right? So temperature is not causing us to consume more water. Rather, there is an intervening variable. There is a mediating variable, thirst, right? So if temperature is going up, but you are not thirsty, you will not consume more water. The temperature is not the reason for consumption of more water. Rather, it is the thirst. Similarly, if you're trying to find out the impact of parents' education on earning, then you will talk about mediation. Right now, we are not interested in the impact of parents' education. We're simply interested what is the impact of a person's education on his wages only. In this case, what will be mediation? You can say education per se doesn't translate to good earnings. Education leads to right attitude and right skills, and that leads to good earning. So those skills and attitude, that will be the mediating variable.
Right,
Okay.
sir. Thank you, sir.
Yeah.
Thank you, sir.
Okay. So that means there is a lot to talk about endogenous variables. In fact, we should spend more time on endogeneity. But unfortunately, I think we can keep on discussing. But remember that endogeneity is a result of something is missing from your model, right? So we started with the assumption, suppose somehow there is a way out to capture your, what we call, confounding variables. If you are able to capture your confounding variables, endogeneity will not arise. Why we have endogeneity? There is something which is unmeasured, which is causing our variable, which is making our variable endogenous. Okay. Let me just show you. That means how would you include the control variables? Let me talk about it quickly. Let's make a model. So let's make a model. Let's call it M5. LM, not LM, because we are running. Okay, just first run the linear regression, then we can run the two-stage regression. How Okay.
Sir, not able to hear you, sir.
Atif sir, you are on mute.
I request the participants to just
Yes, can you hear me?
Yes, sir, you are audible.
Yeah, but somehow there is some problem, like I'm not the host of the meeting, so I'm not able to share my screen. I don't know, it is stopped accidentally, and now I'm not able to share the screen. I'm waiting for the convenience to allow me to share my screen.
Okay. Siddiqui sir.
Yeah, I was called them. That's why I was on mute. I was talking to them only that why have you not allowing me to share my screen?
Okay.
They're saying that I have been torturing you for last 2 hours.
No, it's not like that.
Even it is like that, there are 2 more days.
No, sir, it's okay.
Yeah. In the meanwhile, they allow me to share the screen. You may ask any queries.
Like, if you can spend 1 minute on like difference between confounding and instrumental variable.
Atif sir.
Yes.
Now you are host.
Okay, thank you, sir. Thank you. Thanks a lot. Second. Okay, I believe you can see my screen now.
Yes, sir.
Yes, sir.
Okay, so please confirm.
yes, it's visible now. We are extremely sorry for the technical glitch.
It's
You
fine,
can
it's fine.
continue.
Just kindly ensure that the screen is being recorded. Please, someone confirm, is it being recorded?
Yes, sir. The meeting is being recorded.
Okay, good. Okay, someone asked about that means confounding versus instrumental variable. Confounding is the problem. Confounding is a problem that is related to endogeneity. That what happens, there are certain variables which we do not measure. And these variables impact our independent and dependent variables simultaneously, right? And when you do not include them in the model, then indirectly, though they are not in the model, but they are influencing both. They're influencing our independent variable as well as the dependent variable. This problem is called confounding, and this is what we call endogeneity. So what is the problem with confounding? The problem is that confounders have their own impact on the dependent variable. But when we do not measure them, it appears that the entire impact is because of the education. Means the impact of independent variable seems inflated. It seems exaggerated because the variables which are missing, even their impact will be credited to our independent variable. So we need to find out the true impact, and this is how we use instrument. So instrumental variable are a way to deal with this problem of confounding and endogeneity. Okay. Now, instrument variable in the presence of control variable. Let me just wind it up quickly. So let me just look at the name of the variable. What all we have? Names, data.
So can you share these data sets, sir, as of now?
Definitely, I have shared. I've already shared.
Okay.
Yeah, kindly check your mail.
Yeah, please, sir.
Near C4. Educ. Age. Okay, so let me take just a few variables. One second. Okay, LVage is also there. Tilde, what we have? Education. SMSA. South. Black. Experience. Experience as well as square of experience. Okay. And let's talk about the instruments. What do we have in instrument? Our instrument is near C4. But whenever you include instrument, you have to include all the control variables again. Plus SMSA plus South, Black, Expert, XQ. Let me see. Education. I'm just splitting it. Q. Okay, so all the variables have been included. Let's run this command. Okay. Let's print the output. Tidy. And this M5. Look at this. All these variables, SMSA or South or Black, these all are control variables. We are not interested in their impact. We're controlling for their impact, and we try to find out the impact of education. Education is 0.15, and it's significant. Okay, so this is all from my side regarding endogeneity. So all the assumptions are over. We have covered OLS and 2SLS. Okay, so the next topic that we'll start, it will be time series. So I think we should start it tomorrow. I know that I'm late by at least one day, but what we can do, we can spend less time on univariate. We can talk more about vector autoregression, then cointegration, and then panel data. So if you have some queries, then you can ask, or if you ask me, then I can continue for some more time. But sometimes like people are tired, so they are like not willing to listen to after 1.5 hours. Yes, please tell me what to do.
Sir, I have a doubt, sir. I have a doubt.
Yeah, please.
Yeah, sir. Actually, when you were talking about different slopes and intercepts, so are we not talking like about this random factor model and fixed factor model that we use in
Fixed
econometrics
effects and
sometimes?
random effects.
Yeah, are they same or different?
You can say they are somewhat similar. See, that means the fixed effects and those things. Fixed effects means there is some sort of clustering, right? There is some sort of clustering.
Yes.
Like what happens in panel data, that same person is measured several times, right? Similarly, for 1 year we have data for several firms, or for 1 year we have data for several individuals. So there is time specific effect and entity specific effect. For them also we use dummy variables. We'll cover these topics in detail. We'll cover these topics in detail. We'll discuss about panel data. Yeah. So it was similar to that.
But that is different, no?
Yeah, that
similar.
is different.
Okay, similar.
Yeah.
Yes. Okay. Okay. Thank you.
But one thing that we like mostly do in panel data, that we never use interactive dummies. right? We only have the intercept dummies, right? So they are just the only intercept is being changed, and the impact of the IV are assumed to be constant across all the entities. But here we allowed it to differ. We allowed it to differ for men and women, or maybe for even for region wise. We can find out. That means how does, let's say, in a particular model, how does something is different for people belonging to different age groups? So in that case, you will have more dummy variables. So there will be more slopes, one slope for each category. So we want to find out whether the impact is same for all the groups, for men and women, for people belonging to different regions. We can have two interactions at the same time. Like in the last model, if you remember what we did, it was beauty into gender. We could write beauty into gender into married. So we can have more dummies. That means more nesting. So beauty into gender into married into then race. The person belong to which race, or whether the person belongs to minority, or whether the person is a permanent professor or on ad hoc basis. So you can keep on combining them. You can just keep on multiplying. You can multiply 3 terms together: beauty into gender into nature of appointment into age, whatever. That means you can have several sorts of interaction.
Yes.
Yes.
Thank you, sir. Thank you.
Welcome.
Sir, in time series, you will be covering var, vector autoaggressive, and
I plan to cover univariate analysis first, then the stationarity stuff, then var, then impulse response, how to interpret them, then Johansson co-integration, ARDL.
Okay.
And then whatever time remains, I would be spending on panel data. This was I proposed. In case somebody wants to suggest that I can focus more on one particular thing or other.
We have 2 days, sir. We have 2 days.
Sir,
So
we expect DCC and BEKK also, sir, if possible.
BKK, I'll see. I'll try to see. BKK in R, it was having some problems, but yeah, I'll try. But there is a better model than BKK.
Okay, sir. Kindly, sir. Kindly.
I think whatever contents you have planned, that would be enough, sir. We go according to the schedule.
Okay.
Excuse me, sir.
Yeah, please.
Sir, I'm a student of tourism management. Sir, I wanted to learn, as I requested you before yesterday, sir, I wanted to learn actually how to use multiple data, multiple data. So I request you if...
Multiple data, would you clarify your query?
So multiple data from multiple sources. I mean to say is that if data, one variable, one set is in percentage, second set is in decimals. So data like this, matlab kuch 100.
No problem. See, if you have, do you have that data set with you?
No, sir, I don't have, but I can download it from some source.
So it doesn't matter. See, that means the underlying logic remains the same. You built a regression model. How you make a model? Like in R, it's simply like LM, then bracket starts dependent variable, followed by list of independent variables. They may be measured in any way. Like we have shown, they may be even like dummy variables. It doesn't matter whether they are ratio or percentage, whatever. The only thing is that what you need to keep in mind, recall, yesterday I talked about a specification error. So you can commit a specification error in the sense that, for example, just look at the last model. I included one variable twice, experience and the square of experience, right?
Yes,
so
sir.
you need to be sure whether you need to include experience or square of experience or both, right? So this is the knowledge that you need to understand, that what may happen that initially as experience grows, your income also grows. But after some time, the growth may come down, or the growth maybe that means much more. So depending upon these things, you may think about deciding which variables will enter and in what form, whether they will enter directly or they will enter in the logarithmic form, or they will enter as reciprocals or as squares or as cubes. That means as a researcher of your discipline, you need to decide, think about theory, make some plots, make some descriptive statistics, and then we have to decide. It doesn't matter that one variable is ratio, other is in some other units. Units will of course be different. Think about, you're trying to forecast number of units sold on the basis of rupees of advertisement. Units are different, right?
Yeah.
The number of times something is played. So that means units need not be equal.
Sir, actually, ना sir, कुछ अच्छे journals में सर वहाँ पे डेटा जो होता है वो बिग डेटा होता है, किसी जैसे वर्ल्ड बैंक की रिपोर्ट, जो वर्ल्ड बैंक का डेटाबेस होता है वहां से डेटा लिया, कुछ एक हमने खुद से कलेक्ट किए सर। वैसे अलग अलग डेटा को बहुत से पेपर्स में मैंने देखा है, उसमें उस सबको उनका एनालिसिस करके दिखाया होता है। तो मेरा क्वेश्चन
मेटा एनालिसिस है।
यस सर, तो उस तरह का डेटा सेट अगर आप टाइम सीरीज के लिए लेते
तो मेटा एनालिसिस इज अ डिफरेंट टेक्निक, दैट्स अ डिफरेंट टेक्निक ऑल टुगेदर।
ओके सर,
दैट्स अ different method. What we do, that means आपने अलग अलग papers लिए, you are taking out the effect sizes from several other papers. Paper 1, their R square was 0.5, paper 2 their R square was 0.3. So you just extract all those R square and then you work on that data. That means you do not collect any data, you're simply like getting the results of previous studies and then analyzing that, right? That's meta analysis.
Sir, sir, can you please again tell the name of that package we are using for the robust LM robust that you
Estimate R, ESTIMATR. Yes.
Okay, so estimate R, right?
Estimate R.
So
sir, can we use the standardized values if the variables are in different units or in different ratio, different scales? So can we use the standardized value?
It's your call, you can use, but see, it's not necessary. That means it doesn't violate any of the assumptions, and like in some cases it facilitates your, what I must say, interpretation, but not always, right? It's not compulsory that you standardize.
Okay, sir.
Yeah.
But will it help? But is it better? Will it be easier to interpret in
sometimes, not always, sometimes. For example, look at this. When we estimate our regression model, then what does intercept denote? Intercept shows if all the independent variables are 0, then what is the value of dependent variable? But in several cases, the independent variables cannot become 0. For example, your advertisement will never become 0. Or think about age. Age will never become 0.
Yes.
Or maybe some other variable. There are certain variables which can never become 0. Right? They have to be in positive, like number of employees in a company. How can it be 0? Right? There is no employee. Right? So in that case, it doesn't make sense. So what you do, if you have just like standardize the data, that means with mean 0 and standard deviation 1, in that case, the intercept is like the value for average person. That means, which is not always intuitive. Sometimes it is intuitive, other time it is not. That means, of course, modeling is a science as well as an art. So as a researcher, as an artist, you have to think about which model would be better. Because after all, interpretation is the story that is told by the researcher. Right? Same analysis, people can come up with different stories.
Yes, thank you, sir.
Yes.
So suppose we have created a model, so how will we know that no additional variable we have to take? And we will how we will know that we have taken
talking
the
about a specification error, no?
Yeah. So.
Yeah, that means how do we know? So there are some tests proposed. I think I did not discuss, I forgot. There is a test called reset test. That is a regression specification error test. So there are two ways to do. One thing is that, first of all, your residual plot residual against the fitted values. The pattern in the graph reveals if there is a pattern, most likely you have left out an important variable, or maybe some assumption is violated. So chances are very high that there are some missing forces, missing sources, missing factors that are causing it. And second thing is that reset, RESET, regression specification error test. So let's do this. Let's run this on our model 5. Reset M5. So I'm not sure in which package is it.
This test will tell us that we have missed a variable.
This test will help you. That means no test is foolproof, basically, right? It's a combination of graph plus some statistical test plus your judgment, right? So, but yeah, that means they can point out that there are some, whether there are certain anomalies or not. Let me see if reset is there, or is it in LM test? Let me see. Not this one. 1 second. Let's make that model. We have this model 1. Let me see. Okay, look at this. You see what is the p-value?
It's
P-value
more than
0.99.
Yeah.
So it means that there is no specification error as such. This model suggests, though we have included only one variable.
What is the null, sir, here?
Null hypothesis is that basically what the reset test is doing. Reset test is regressing the residual against all the independent variables and then against the square and the cubes of fitted variables. So that means whatever we are looking graphically, it is doing the same thing mathematically. So null hypothesis is that the additional variables are not significant. The additional variables, if they exist, they will be captured in the predicted values. So their square would be capturing or serving as proxies for missing variables. So it means the coefficient on those variables is 0. So null is that there is no specification error. Alternative there is. So the null could not be rejected because p-value is this. Let me just show you 1 second. Like, see, if the test is not rejected, there is no guarantee that there are no missing variables. But if it is rejected, then there are very high chance that there are missing variables. Are you getting?
Yes, sir.
It's something similar to that null hypotheses are never accepted. Either you reject them or you fail to reject them. Right? So here null is not rejected. Right? We could not reject. Right? So make this use this reset test.
So sir,
in
we
combination
have
with
2 options, that is regression specific test, that is reset test, and this residual
plots.
plot.
Yes. So
So
most likely they are
what about residual plots?
Sorry?
So how do we do residual plots?
Residual plots, it's very easy. Look at this. So where was our data? This data was X. So look at this. What you do, you need to first generate residuals. Okay. You can do it directly, but there is a very nice function for it. Simple and nice function. So make a new variable. Let's call it X2. Augment X with X1, right? So I'll show you what X contains and what this X1 contains. X and X2. Okay, let me show you. Names X. You see? You see, dot fitted, dot resid, dot sigma, dot cooks, dot std, dot resid. So these all are additional variables. Let's make a plot of it. I've given the codes already, but we can plot ggplot. Data is X2. And what we are plotting on the x-axis, we are having fitted. On the y-axis, what we want? Resid. And what we want? Let's say GM point. Okay. So you see in plots, there is a plot of fitted versus residuals, right? If this does not make a specific pattern, most likely all is well. Means it should look like a random plot. If there is a pattern, like there is some curve, some upward, downward trend, if you're able to see some trend, then there are chances something is missing. And again, this is an art. Same people looking at the graph, they may come up with different conclusions. Some person might see, oh, this seems to be like flaring at one side. So this is how this graph have to be interpreted in the light of your other tests.
So no correlation, sir. Standard residuals and fitted residuals.
Yeah, they seem to be like randomly dispersed. In that case, it seems to be okay. Right? Diagnostics. So,
basically, those two should not be correlated.
Yeah, they should not show any pattern. Yes, should not be like positively or negatively, or maybe no curvilinear relationship should be there. So basically, pattern should not be there. If there is no pattern, that means yeah, they are independent.
If there is a pattern, sir, then
if there is a pattern, means there's something is wrong.
Okay.
Either assumptions are violated, or maybe some important variable is missing. Most likely.
Okay. Okay.
Most likely, some important variable is missing. Yes. And see, I'm just forgetting the name. That I think it was a Nobel laureate. He once said that every model is wrong. Every model is wrong. The only thing is that some models are useful. Models सारी गलत होते हैं. Just some models are useful. So whatever model you make, there are, of course, various left out variables. So what you do, and see, not only statistical grounds, theory is the main driving force. When you're reading your literature, people are arguing, suggesting something. So that means that collective wisdom, theory. So theory is the, and see, in several cases, there are competing theories. There are competing theories. One group of people believe that these are the determinants, or the other group may believe that these are the determinants. So you can test which theories hold in what case. So for example, in finance, you can say that Indian firms, maybe small firms may be following the model, or the large firms, they may exhibit the behavior of pecking order theory. Similarly, in marketing, there are different models of consumer behavior. In one industry, consumers are behaving according to one particular model. Any specific queries, because people are from diverse backgrounds. So I would like to clarify if they have some specific questions, and even suggestions, like how can we make the other remaining two sessions better, in case you have a query. Else
Sir,
we should wind up. Yes, please.
sir, yesterday you talked about errors of measurement as one of the reasons of exogeneity. Sir, sometimes we have to go for secondary data and we have large number of observations, so we cannot test we cannot see each observation. So is there any way through R that we can identify the missing values or the outliers in a large data?
These are two different things. Missing values and outliers are totally different things. First of all, when we say outliers, then outliers on what? You see, when we talked about outliers, then I talked about outliers in the context of model diagnostics. After you have estimated a regression model, then you want to find out, is your model accurate? Means your model will be accurate if it does not produce very large errors. If it produces large errors, either the model is inaccurate or there are some outlier cases. See, for most of the cases, the model is fitting well. Just one or two cases, they don't fit well, right? So this is the concept of outliers. Otherwise, if you simply take a variable, right, and you want to classify it in terms of outliers, then I think it's not a good idea. But if you want, then we make use of box plots. You can make a box plot which is based on 5 values: median, minimum value, maximum value, and the quartiles, right? So then, like, we have certain limits. If something is beyond those limits, then we can call them that, yeah, they seem to be outliers. They seem to be very different from the data, right? So we make like this based on interquartile range. So you can make box plots and can think about outliers for every variable. But generally, we do not do it. Just fit the model and just proceed with it. And yeah, regarding missing values, there are several functions that do not work in the presence of missing values. You need to drop those rows, delete those rows, or impute those, right? So dealing with missing variable is a totally different topic. There are like several philosophies. How do you deal with them? You can omit them altogether, drop them altogether. You can impute them. Impute means replace those values through some mechanism, through some regression procedure, or through some other method, right? There are several ways of like filling those missing values. Either you fill them or you drop them.
Yes, sir.
Yeah. So if you find out like if there are missing values, there are specific functions. For example, right now I don't have. Tomorrow I'll show. When I'll be talking about time series, there you will find so many missing values. I'll show you quickly how to find out like which series has how many missing values.
Yes, sir.
Yeah, I plan to start time series today itself, but unfortunately what we plan, rarely we are able to achieve it. So should we wind the session for today?
Sir, I have a doubt.
A few more queries quickly. Yes, please.
Sir, in model 5, you have used after X per SQ, instead of plus, you have used some vertical line. Sir, can you please tell me what does it mean?
Vertical line. This vertical line, after the vertical lines, I have written out other variables. These are the instruments.
Okay, sir.
So whenever you are using two-stage least squares, this is the way to do it. So our main variables are before this vertical line, and after the vertical line, these are all instruments. So
sir, if we are using control variables, so then also we have to use this, or just simply by putting plus
See,
we can write our control variables?
if there is endogeneity and you want to use two-stage least squares, then you talk about this vertical line. See, why we have using this, compare the list. Look at this model. There are some variables before the line, some variable after the line. There is one extra variable on the right hand side of this vertical line. That is near C4. All other variables are same.
Yes, sir.
EDUC has been replaced by near C4. So near C4 is serving as an instrument of EDUC. All other variables are serving as control. But if there is no endogeneity, there is no need to go for this IV robust model. Simply use LM or use LM robust. Okay.
Okay, sir. Thank you, sir.
Yeah. This is two-stage least squares, right? Then there is three-stage least square.
So one more question. So in the model 5, there are two variables, experience and square of experience. So that doesn't make the model multicollinear?
No, see, multicollinearity is a linear concept, right? If you are using experience and 2 into experience, they will be linear. Square is a curvilinear relationship, right?
Yes, sir. Yes,
So,
sir.
yeah, that is not multicollinear. Linear means there is a linear relationship, but experience and experience square, there is a quadratic relationship. So this does not violate the assumption of multicollinearity. No.
Yes, sir. Thank you, sir.
Multicollinearity means there should be no linear association, no perfect linear association. Okay.
Sir,
Thanks. Yeah, please.
Tomorrow,
Please.
tomorrow kindly cover VAR and Johansson co-integration, sir.
Sure.
Day after tomorrow panel data. So
Okay.
if you like stick to this schedule, then that would be
Sure.
helpful.
Definitely.
Thank you. Sir. Thanks a lot.
Okay, take care. Thanks for this patient listening.
Thank you, sir.
Thank you, participants. Thank you so much, Atif sir. I hope you all are enjoying the interesting session by Dr. Atif sir.
Yes, ma'am.
Yeah, definitely.
Okay, thank you so much. We are keeping a track of the attendance and you may join tomorrow as per the schedule time. Thank you so much.
Thank you, ma'am.
Thank you.
Thank you, madam.